Hi everyone. Let's review the circles and angles assessment from last week. Number one was a bunch of angle calculations. Most people did fine with that. Let's talk about two. So I saw a lot of great work on number two, but there were a few comments I wanted to make. So first of all, 2a, explain why angle ACQ is congruent to angle APQ. Some of you did quite a bit of work actually computing the measures of these angles, which worked out just fine. But none of that's necessary because the key is that both of these angles intercept the same arc. They intercept arc AQ right here. And the inscribed angle theorem says that the measure of an inscribed angle is half the measure of its intercepted arc, and a corollary of the inscribed angle theorem then says that if two inscribed angles intercept the same arc in a circle, then they're congruent. And that's all you had to say here in 2a. 2b, I saw tons of great work. I saw probably at least 20 different proofs of the fact that ABPQ was a rectangle. Some of them were very long, but very good. I had in mind a rather short proof, but as is often the case, what I had in mind wasn't exactly what students had in mind. So some of your work was much longer than I intended. I apologize for that. It's not my intent is not to assign proofs that will require, say, 200 or 300 words to explain. But your work was excellent, and I saw lots of really creative approaches. Let me just show you sort of what I think is the cleanest approach to this. And that is simply, you know that this is an equilateral triangle, so these angles are 60. So the measure of arc AB is 120. In fact, all of these arcs are 120. Because these are midpoints, each of these arcs is 60, and so that means that this arc is 60 plus 120, which is 180, and this arc is 60 plus 120, which is 180. That makes these things semicircles. And if that's a semicircle, then this chord is a diameter, and this chord is a diameter. So by that argument, these two things are diameters, but these are the diagonals of the quadrilateral. All the diameters in a circle are congruent, and diameters intersect at the center, which also bisects the diameters. Therefore, the diagonals of this quadrilateral are congruent and they bisect each other. Therefore, it is a parallelogram because the diagonals bisect each other, and it's a rectangle because the diagonals are congruent. So again, I saw lots of terrific work on this, but this was the simplest, I think, way to proving that I had in mind. A lot of you actually used the bonus as part of your proof of 2b, which was terrific. And the bonus is actually pretty easy to prove. This is called a cyclic quadrilateral. A cyclic quadrilateral is a quadrilateral that is inscribed in a circle. And in fact, any polygon that's inscribed in a circle is called a cyclic polygon. And cyclic quadrilaterals have an interesting and useful property, namely the opposite angles are supplementary. And the reason for that is if you look at two opposite angles, x intercepts this arc, and z intercepts the complementary arc. So these two angles together intercept the entire circle. The entire circle has measure 360 degrees. So both of these angles together amount to half of 360 degrees, which is 180 degrees. So these angles are supplementary. Just lastly, one issue that a lot of students had with this problem was simply drawing these diagonals in and assuming that they were diameters, assuming that they passed through the center. And I just want to make clear that if you have a quadrilateral in a circle, it's not obvious that the diagonals of that quadrilateral pass through the center, right? Here's one such example. It's something specific about this construction that makes these pass through the center, and that is something that you have to justify when you're proving this.